Hello, today we're going to be talking about Math 3, Unit 7, Lesson 7.4, which is going to be about sideways parabolas. But my first piece of advice to you is to not let the kids know that. Let's just start with, in general, a question: what happens if the directrix is vertical? Get them to wonder. Yesterday we went through that whole big long experimenting with if we had a given point and a given line and we wanted to try to find all the points that were equidistant from those two, what shape would that make? And they figured out after some time that that would be a parabola, and they found the general equation of that parabola if the vertex was at 0, 0. And all of the directrix that we gave them were horizontal lines. So the question then is, what happens if it's a vertical line? And so just for your teaching, I'm going to show you this first, my follow-up questions. So I would pose that. My personal style is I'd have that question on the board, and I would have them talk with their partners, have a little piece of paper where they drew some stuff, whatever they wanted to do. They could sketch and guess, they could use equations, whatever they wanted. What did they think was going to happen to the parabola when it's vertical? And some questions to kind of prod them along is, how's that going to change how the graph looks? Maybe they'll think of graphing. How's that going to change how the equation looks? Eventually we're going to get to that. I think how the graph looks is the way that I approached it first. I'm a very visual person, so that's probably how I would start with. And then after a lot of talking to them about those things and discovering the answers there, we're going to want to ask them, what would we do to the equation to make the parabola face left? And what would we do to the directrix and focus to make the parabola face left? I think those are all a good set of questions to pose to drive your lesson. Because first you want them to wonder what the answer is and then give them the answer. So let's just look at how that might start. If we wonder what happens when the directrix is vertical, the first thing I would do is explore graphically. Now, I would like it if my students in pairs or threes, if they sit in threes, came up with some conjectures. And if I could get a class that was talkative and would do that, if I could poke and prod them by asking them questions and giving them a few minutes, I would take a list of conjectures. What do you think? So what do you guys think? Let's write them all down. And over on the side, the board that I don't use very much, I would make a list of conjectures. And I think that this will happen or that'll happen, and whatever they say, it would be wonderful if somebody had the correct conjecture, but I'd go ahead and write those down. If I get a class that just nobody, no matter what I poke and prod I can do, then I would do all this exploration together. Well, how about we make a graph? If the directrix is here and we want our vertex at 0, 0, and remember, the parabola is a set of all points that are equal distance from the directrix and the focus. Where do you think the focus would have to be? And remember, we go vertical distance, so this is 3. So if I went 3 on the other side, hopefully they'd pick up that the focus should be here at 3, 0. And I would ask them what do they think the equation of this line is. Hopefully they remember that that's an x equals line, but the things that I usually do is, well, every point on this line starts with -3. This is -3, 0. This is -3, 2. This is -3, 7. This is -3, -2. All of these have an x value that equals -3, and that's the equation of that line because that describes every single point on that line. So there's our focus on our directrix, and we are wanting to find points that are an equal distance from both of those. And one of them that they should be able to come up with is this vertex at 0, 0. And when you ask for more, hopefully based upon the exploration they did before, they would say, well, it's going to be 6 between the directrix and the focus. So if I go straight over, then what I want to do is go over 6. Let's see, 2, 4, 6. Then this would be a distance of 6. And this would be a distance of 6 because 3 and 3 make 6 altogether. And so that should definitely be a point. And then you remember how we had that symmetry going last time? Can you think of how the symmetry would work this time? And hopefully they'll come up with down here at 3, -6 would be another point that would be equal. And from here, I'm hoping that they might think about it being a sideways parabola. To hit all of those and have that symmetry, the same points up here as down here, we end up getting that sideways parabola. So exploring graphically, they should discover that it's a sideways parabola if the directrix is a horizontal line. By the way, a really interesting exploration that I have not done, but I would push my high-end class to, is what happens if the directrix is a diagonal line. I know myself that equation comes out with an XY term in it. I definitely wouldn't throw that at the average kid who we're just hoping learns the material that we're covering. But if you would like to inspire one of your higher end students who's bored in the class with a bunch of kids that you have to go real slow for, you might say, one thing that I've never explored is what happens if the directrix is a diagonal. I sure wish somebody would play with that and figure that out. And usually there's some kid who'll take that on. We may get ourselves into more math than we intended, but I'm really excited for them to wonder and explore. So we explored graphically, and what we discovered is we get a sideways parabola. We might ask, what would we want to do? So we know how it happens that a parabola faces up and that a parabola faces down. We know how it happens that a parabola faces to the right. How does it happen that, how would the directrix and focus be arranged to have the parabola face to the left? And hopefully someone might think of that the focus would have to be over here and the directrix over here, and you should get that. So we now know that this would give us a sideways parabola, but we don't know what the equation would look like. Can anybody think of how you could write an equation for something like that? And they really don't have the tools for that yet. Again, it'd be interesting to see what people hypothesized. You might see if anybody's original conjecture was that the parabola would be sideways, you might recognize that person now if you wrote those conjectures up. Okay, so the next thing I would do is explore it algebraically, and let's find out what happens to the equation. And so here we have our directrix at x equals -3. Here we have our focus at 3, 0. We're going to take a standard point xy that's going to be somewhere on our parabola, and we're going to derive the equation of the parabola. Now what this does, here's the worksheet that they're eventually going to do. They have a lot of graphing and finding everything, but at the end of the worksheet they have two where they have to derive the equation of the parabola. So all right, so in this one, we want, remember, for the point to be an equal distance from the focus to the directrix. And we talked about when you go to the directrix, you go straight there, perpendicular to the directrix. This time it won't be straight down because the directrix isn't down here. It'll be straight across. The perpendicular distance is always going to be shorter than a distance to the side. Boy, just saying that made me want to ask why. Why do you think that would be? And hopefully they could see a right triangle that the hypotenuse is always going to be longer than this long leg, and so that's why any other distance other than the perpendicular distance is going to be longer. So anyway, we have a point now on the directrix that we're going to use, and that point I'll call D, and it is definitely back -3. But there are a lot of points on D, depending upon where this point is. Remember, we went straight over, so the one thing that we can say is that whatever this y value is, this is going to be the same y value. They are at the same exact height. If we're up 7, then this will be up 7. And so since this we put y, this we will also put y. Okay. Another point over here would have a different y, but it still would be -3 and that same y. Okay. So now we're going to try to find this equation, and the fact that we used yesterday to derive the equation is that the distance here from P to F has to be equal to the distance here from P to D. Remember, the definition is that a parabola is the set of all points equidistant from a given point and a given line, equal in distance from the focus and from the directrix. So we're going to find these two distances and we're going to make them be equal. And so for the distance from P to F, I'm going to use the distance formula on these 2 points. And I would probably call on a student to help me set this up. So I always point at these 2 points as we do it just to help them focus on what they're looking at. So from P to F, would be the difference of the x's squared plus the difference of the y's squared, and that would be the distance from P to F. If we knew that exact point, we'd just plug in those numbers and we'd be good to go. Right now we're doing a general point, so we get a general equation. And the next distance we want to know is from P to D, so these 2 points. So again, I'd point at them, and I would call on a student to help me set this up. So I need the difference of the x's, that'll be x minus -3, and the difference of the y's, y minus y, aka 0. And then we're going to solve that algebra. So we're going to square both sides. The squares will go away, and I'm going to go a little bit faster than I would for my students. I'm going to square and clean here and have x squared minus 6x plus 9 plus y squared. And over here, I can't help but be a teacher and do that. And I'll have x squared plus 6x plus 9. And this would be 0, and 0 squared would still be 0. And now as I clean these up, I'd subtract x squared from both sides and they would be gone. I'd subtract 9 from both sides and they would be gone. I would like to get these two x's together, or these x terms together, so I'm going to add 6x over here. And on this side, all I'll have left is y squared, and on this side I will have 12x. And that's a perfectly good form of the equation. I would asked the kids yesterday, it seemed like we got an equation when we derived to be x squared equals 4cy, and so what do we see that's different? And now in this time we had the y being squared. A lot of us then rearranged and divided over so we could have the y by itself like what we're used to. That's an alternate form. For your information, this form right here is called focal width form because it's very easy to find the focal width. The focal width is in fact 4c, and so it turns out that in this particular case the focal width will be 12. That is the width at the focus will be 12. And if we were going to graph this parabola, as a matter of fact we did on the last page, let's turn back a page and see what we got. We're going to graph that parabola. At the focus we should see a width of 12, and in fact that's what we had, right? We had 6 and 6 is 12, the focal width is 12. So that's called the focal width form. It's really handy if someone's asking you the focal width or the focus or the directrix. And then this other form where we had the y by itself. In this case, I guess it would be the x by itself, right? If we got this one by itself, it would be x equals 1/12 y squared. We liked it when it was this way because our intuition kicked in, and this said us this is really wide. It's got a fraction in front of the squared term. It's just we're not used to seeing the x by itself. Oops, sorry, I'm off the screen. We're not used to seeing the x by itself. It's definitely wide. Normally this being a 1/12 would tell us, oh, this is a really wide parabola facing up because that's positive. This is a little bit out of what we learned before, so this will suddenly feel a tiny bit less helpful. But this form, or this form, is going to be known as the descriptive form or the vertex form. And those, descriptive. Those will be more helpful tomorrow when we switch the vertex from 0, 0. So let me just show you. This worksheet is in Google Drive, and it goes through the 3 possible forms. Remember, one of our focuses for this unit is for students to be able to fluidly move from form to form, to be able to see things that they're interested in. So when you get something in general form, let's just look at the ones we're normally used to, these guys. When you get something in general form, there's not really much you can see. I can know that if A is positive, it's facing up, and if A is negative, it's facing down. That's about it. When we had things given to us in vertex form, that was really handy. It was easy to see the vertex. It was easy to know whether it was facing up or down, and it is in fact the most commonly used form. We can't skip this form because this is the form they're most likely to see something on later. But the focal width form, in fact, the book that I was using at Clovis West last year in Algebra 2, used this form for their parabolas. So it's not something that we're just inventing. It is something that's out there. And I still can spot the vertex. We'll talk more about this in 7.5. And I can still tell whether it's facing up or down based upon the positive or negative here. But now it's also easy for me to know the distance to the focus and the directrix, and it's easy to know the width of the parabola. So this is a real handy form, and so it's nice sometimes to have things in the squared by itself kind of form, because squared by itself will make it very easy to see the focus and directrix. We'll talk more about this at the end of these notes. Right now, you personally should decide which one of these two forms are you going to live in primarily, and then direct your students to change to that form every time, because right now their understanding is really fragile, and they're probably not fluid enough to change the way they think about the problem each time depending upon the form it's in. So pick one of them. I'm going to probably use this focal width form a lot right now, and then let them develop their understanding of when you get the more common form as we go on through the chapter. I think the math is a little easier this way, so that's why I choose, but it really is not so much easier that it's a big worry. Okay. All right, so the last thing to talk about is form. And so on the worksheet today, you'll see that some of them have the squared term by itself, and some of them have the not squared term by itself. And so whatever you've decided is the way that you're going to favor out of those. If you wanted to see the forms, if you wanted to talk to your students about the names of the forms, then this is, that other worksheet is probably not ready yet because it shows the shifts from 0. General form we'll talk about tomorrow, but vertex form is the form where you get the not squared term by itself. And the focal width form is where you have the squared term by itself. And you want to decide that you're going to live at one of those two, but you do want to have the students start to know these two words, because in the directions, let me just show you that. In the directions on this worksheet, right here it says derive the equation in vertex or descriptive form. So what that would mean for me on the last problem I did, let me show you that last problem, is that I would not want to stop there because that's the focal width form. I would want to get the not squared term by itself, and that's the vertex or descriptive form. And your CDT team decided it was better to start practicing moving between forms earlier so the students would have more time to get that. But I would tell you right now, pick one of the forms and focus on it as students are trying to solve problems like this, because as they're solving these problems, it'll be good if they do it the same every time. So I'm going to use the focal width form, which is get the squared by itself. And that will give me that the coefficient here will be 4c. So here the squared is by itself. This will be 4c right here. And this is not a very nice problem. Somewhere in your work in the first 2 days, you need to do one that's not a super nice problem. This one's especially bad. I maybe could have made it a 6, so at least I had 6/4. So I have c equals negative 5/4, or if you'd like, negative 1.25. Okay, and then if I want to know, I'm going to draw a little sketch because I find that so much easier. The distance from this vertex, the distance to the focus is going to be negative 1.25. So this is 1, this is 2. It's going to be right there, negative 1.25. That'll be my focus. So I'm going to put, now that I have that there. And how did I know it was, oh dear, I think I wrote these I wrote these backwards because I made the x squared instead of the y squared. Ah, silly me. So let's just change those two problems. So I'm going to turn a couple pages here. And this whole page will be with the y squared, and then we'll mix them more later. You'll notice on every one of these problems you have the y being squared. So I'll actually just use some of these for example. So here, when the squared term is by itself, what I'm going to do is I'm in focal width form. The squared term is alone, so I know that 4c equals 8, and that makes c equal 2. And so since the y is squared, I know it's either this way or this way. Since the 8 is positive, I know it's facing toward the positives. And so I will go, c is positive 2. That's another way to know I'm facing there. So there's my focus at 2, 0. My directrix is then going to be back 2. There's my directrix at x equals -2. I had to think for a minute that all the x's were staying the same. And my focal chord endpoints then, the width of my parabola is just going to be 8. So that means from my focus I need to go 1, 2, 3, 4, and 1, 2, 3, 4, a total width of 8, right? And this will be my parabola. You might like to have your kids label a vertex, because when you have all these points not labeled with anything, it would be easy to draw the vertex here or here, lots of different other places. And so my focal chord endpoints were 2, 4, and 2, -4. Okay. At some point you might want to mention to ask your students, is this a function? And they should realize it's not a function, but that's fine. Okay, now we have a couple with fractions. I'll go ahead and use this one because it's a negative and I wanted to do a negative example. So this one, is this one in focal chord form? No, it's not, because the squared is not by itself. So before I start, because focal chord form is the form that I'm going to choose, I'm going to multiply both sides by -2, and I will have -2x equals y squared. And just for my own self, I'm going to rearrange that. That means that this is 4c. So 4c equals -2, and c is -1/2. Now, c being negative means my focus is going to go backwards. So here is my, again, y is squared, so it's either going to be this way or this way. C is negative. I'm going to go back 1/2. There it is. That's my focus. So my focus would be -1/2, 0. And for my directrix, I'm going to go forward 1/2. So it'll be this guy, which is x equals 1/2. And my focal width is this number right there. That's my width. It's 4c, and so it's 2. -2 is kind of a hard number to think about for a width, but it's 2, so maybe we should say the width is the absolute value of that. And so that means I need to go up 1 and down 1. This is a much narrower parabola than this one. Okay. If we had put both of these into vertex or descriptive form, we would have had x equals 1/8 y squared, and here we had x equals -1/2 y squared, and it would make sense to us that 1/8 would be a wider parabola than 1/2. We have that idea that fractions are wide, but this being a smaller number is even wider. And so just going back, our focal chord endpoints were back 1/2 and up 1 and back 1/2 and down 1. And so that's how that would go. Okay. So you can see we're starting to mess a little with the two forms. Pick one of the two forms that you're going to live with. If I was constantly teaching this form, if this was the form that I was preferring, here's one in that form, then I would be teaching my students to take the reciprocal. I would be teaching them get the not squared by itself and take the reciprocal of this to find the width. So I would know that 4c equals the reciprocal of that, which is 4. And then I would get c was 1. And on this one, I would have had to solve it into this form if I was focusing on this form, and then I would say 4c is the reciprocal of this, so it's 8, and then I would go. So the math then becomes exactly the same. You just need to focus on the fact that it's the reciprocal if you're going to be working in this form where the not squared term is alone. Okay, so get that straight in your head. Do it one way for your kids. Have them always move it to the squared alone, or always move it to the not squared alone, so they're always moving to focal width form, or they're always moving to vertex form for this first day. When they do the last part, this part where it says to get it in vertex form, that's just to make sure that for people like me who've only done the focal width form, the students realize that they can move that on and do that last step. So let me just show you again what that last step was. That was, once we had this focal width form, then we divided by the 12, and now this is in vertex form. So they will do this exact same math, these same 3 steps of math, and then at the end to get it in vertex form, they will want to get the not squared letter by itself, and so that would be dividing by 12. Okay, so that's the last thing to talk about is those 2 forms. If you're consistently using focal width form, the only thing you need to talk about vertex form is about is on the last 2. It says put in vertex form, and vertex form is